The European Space Agency has recently unveiled a new set of images from its ExoMars orbiter, and they may provide the sharpest look yet at the mysterious interstellar visitor nicknamed 3I Atlas, an object that has quickly become a magnet for global scientific curiosity. First detected on July 1st, this unusually bright body from beyond our solar system has baffled astronomers not just because it is rare, but because it behaves in ways that strain familiar categories. Harvard astrophysicist Avi Loeb, among the most prominent voices studying such anomalies, has called it both fascinating and perplexing, a careful choice of words that reflects how little the usual templates seem to apply. When ExoMars captured the object on October 3rd, as it passed within about 29 million kilometers of Mars, the resulting view showed something that looked more like a luminous sphere than a typical comet, a compact, glowing ball with only a faint extension and none of the obvious dust and gas tail expected from an icy body warming near the sun. The new observations closely echo images taken earlier by the Hubble Space Telescope in late July that first hinted at the object's odd nature. And the similarity is striking because ExoMars' camera is far smaller than Hubble's 2.4-meter mirror. Even so, ExoMars still recorded a conspicuous signature, a tight, bright core inside a soft halo roughly 2 pixels wide, while the background stars remained crisp points, confirming that the glow is not a camera artifact or optical trick. That detail matters because it suggests the light is intrinsic to 3I Atlas rather than being sunlight reflected from nearby debris, and it implies the object has stayed relatively compact, even while diving deeper into the inner solar system. There is reason to think even sharper data already exist. NASA's Mars Reconnaissance Orbiter reportedly aimed its high-rise camera at the object during the same close passage, and HIRSE's half-meter telescope can resolve features down to around 30 kilometers per pixel, potentially enough to reveal whether the surface reflects light smoothly like rock or irregularly like metal. Yet those images have not been released, reportedly because a government shutdown froze much of NASA's communications and data sharing systems. Researchers who coordinated the observations say the data were taken at exactly the right time and are believed secure within institutions awaiting processing. But for now, they remain inaccessible, and the silence has become its own fuel for speculation. Whenever cosmic intrigue collides with bureaucratic paralysis, imagination rushes into the vacuum. Online observers have wondered whether the delay hides something extraordinary, even a faint possibility of an artificial origin, while others point to a more mundane explanation. Policy and politics on Earth routinely slow science, even when the universe is handing us a gift. Whatever the cause, the truth is momentarily locked away in encrypted files circling Mars, leaving scientists to work with what ESA and Hubble have already provided, and even that is plenty strange. Unlike ordinary comets, 3I Atlas shows a glow that appears to stretch toward the sun rather than away from it, an inversion of the expected direction for dust and gas streaming from sublimating volatiles. If sunlight were simply boiling off ices, the tail ought to trail behind the object, but this one seems to brighten or extend sunward, as if driven by a process that current comet models do not neatly explain. Its brightness has also stayed remarkably steady over time. A conventional comet nearing the sun typically flares as heat triggers cascades of vaporization, producing a dramatic, evolving tail. 3I Atlas, by contrast, has maintained a smooth, rounded profile across multiple observations, with none of the noisy variability that usually accompanies active outgassing. Then there is the orbital geometry, which adds a second layer of improbability. The object's path is unusually aligned with the ecliptic, the plane in which the solar system's planets orbit. Most interstellar visitors arrive on random trajectories, plunging in from high above or below the planetary plane because they are unbound wanderers from distant stars. Slipping along the ecliptic suggests either a remarkable coincidence or some selective mechanism shepherding its approach. A natural interpretation is possible. Perhaps the object was gravitationally shaped by another star system's debris disk before being ejected into interstellar space. But statistically, such alignment is uncommon enough that it raises eyebrows, and for some theorists, the precision feels unsettling, like a path that was designed rather than stumbled into. The mystery deepens when size is considered. Preliminary brightness estimates imply 3I Atlas may be far larger than previous interstellar objects such as Oumuamua and 2I/Borisov. Those earlier visitors were likely on the order of hundreds of meters across. This newcomer could span several kilometers, a scale that makes it a singular opportunity. An interstellar body that big and bright is a rare astronomical treasure, close enough and luminous enough for detailed studies by both ground-based observatories and space-based instruments. Its bulk also raises questions about how it survived the trip. To cross interstellar space intact, it must be structurally robust, able to endure countless impacts with dust grains and atoms at immense relative velocities without crumbling apart, which again pushes scientists to think about unusual compositions or histories. The coming months promise an escalating test of its nature. On October 29th, it will reach perihelion, its closest approach to the Sun, where intense radiation and heat should provoke clear activity if volatile ices are present. If it is a conventional cometary body after all, perihelion ought to awaken jets, dust clouds, or other signs of sublimation visible even from Earth. By December 19th, it will pass closest to Earth at roughly 1.8 astronomical units, still distant but close enough to refine light curves and spectra. Then in March 2026, it will glide within about 54 million kilometers of Jupiter, potentially giving NASA's Juno spacecraft the chance to attempt distant observations. Each waypoint offers a different observational angle: photometry to watch brightness changes, spectroscopy to probe surface chemistry, thermal readings to infer internal structure, and high-resolution imaging to test whether it is irregular, elongated, or smoothly spherical. The scientific community is tracking all of this closely because interstellar objects are not just curiosities. They're time capsules from other planetary systems, fragments of alien worlds thrown into the void by collisions and gravitational upheavals. Studying them lets astronomers sample the broader chemical diversity of planet formation across the galaxy and compare it to what we see in our own neighborhood. Yet even by that lofty standard, 3I Atlas stand apart. With its odd brightness behavior, its sunward glow, its near-ecliptic trajectory, and its apparently large size, it is unlike any interstellar visitor observed so far, and theorists have begun building a menu of possible explanations that range from conservative to speculative. One idea is that it is a fragment of a planet or moon ejected violently by a gravitational slingshot, leaving behind a surface baked hard and reflective, perhaps capable of producing the observed glow through exotic mineral fluorescence or thermal effects. Another suggests a dense metallic remnant of an ancient asteroid whose lighter materials were stripped away over eons of interstellar erosion, leaving a compact, high-albedo core. More adventurous hypotheses entertain the notion of technology, perhaps a derelict probe or engineered object drifting for ages between stars. That option is far-fetched and remains outside the mainstream, but proponents note that it is not conjured from nothing. It emerges because the data refuse to sit comfortably inside normal comet boxes. No conventional tail, a glow oriented the wrong way, a trajectory that seems improbably tidy. Sorting among these scenarios will require precise light curves, measuring how the object's brightness evolves over time. If the light rises and falls periodically, that would hint at rotation in an irregular or elongated shape, leaning toward a natural origin. If the brightness remains unusually stable, it might indicate a symmetrical form, still not proof of design, but a clue that would need explaining. Spectroscopy will be equally decisive. By splitting the object's light into wavelengths, scientists can look for signatures of ice, silicate rock, metals, or more exotic compounds. Even faint absorption bands could radically narrow the field, revealing whether the surface reflects sunlight like a dusty comet, a bare rocky shard, or a metallic body. Beyond the immediate puzzle lies a broader, sobering lesson. Humanity has no standing framework for managing interstellar discoveries. Each new object triggers an ad hoc scramble among agencies, universities, and observatories to observe it before it escapes, and the first of its kind, Oumuamua, came and went before most facilities could even point at it. 2. I/Borisov offer a bit more time, but still only a narrow observational window. 3. I/Atlas provides a longer and brighter opportunity, but only if international collaboration keeps pace and data flow remains unhindered. Some scientists argue for a permanent global committee, possibly under a planetary defense or space science umbrella, to coordinate observation strategies, evaluate risk, however small, and ensure rapid sharing of measurements. A distributed network of observatories across both hemispheres could provide constant sky coverage so fast-moving interstellar bodies do not slip by unnoticed. Such a system would also strengthen early warning for objects that come unusually close to Earth, whether they are natural fragments or something stranger. The projected cost is large in human terms, but small against what is at stake. Building a Northern Hemisphere counterpart to Chile's Vera C. Rubin Observatory, for example, might be on the order of $1 billion, a fraction of daily global military spending and within the scale of a single national research budget. The argument is simple. Detection and understanding are cheap compared to ignorance if a future visitor ever posed even a remote threat, and even when threat is not in play. The scientific payoff is immense. Encounters like 3 I/Atlas also prod the oldest philosophical question. Are we alone? If an object were ever confirmed to be artificial, the cultural and historical consequences would be beyond measure, a moment that would redefine humanity's place in the cosmos. That possibility remains remote, and the prevailing scientific posture is rightly cautious. Most evidence still points to some natural explanation, even if unusual. Perhaps an uniform heating drives jets from shadowed regions in a direction that only appears sunward, or surface materials fluoresce under solar radiation in a way that mimics a reverse tail, or perhaps the ecliptic alignment is simply a statistical outlier we were bound to see eventually. Still, even conservative readings leave 3 I/Atlas as a marvel, a massive, pristine shard from another star system visiting ours for the first and perhaps only time. As it proceeds along its path, professional telescopes and space probes will continue to watch, while amateur astronomers organize coordinated campaigns to help fill gaps in coverage. Every new datum will feed models of interstellar population density and refine estimates of how often such objects enter the solar system. Some calculations suggest that hundreds might pass through each year, most too dim for our instruments, meaning the few we detect could be only a bright crest atop a vast, invisible river of wandering debris. When the delayed high-rise data finally reach the public, they may answer some of the most urgent questions by revealing surface texture, rotation, and shape. Infrared observations could show temperature variations hinting at internal composition, and combined with continued optical tracking, scientists may be able to determine whether 3 I/Atlas is solid or porous, icy or metallic, ordinary or exotic. Yet, even with perfect data, interpretation will not be automatic. Cosmic visitors have a habit of expanding the categories we use to describe them, forcing revisions to theories that once felt complete. In that sense, the story of 3 I/Atlas is not only about a foreign object sweeping past Mars and the Sun, but also about how a species on a small planet responds to the unknown, with curiosity, caution, argument, imagination, and sometimes frustrating delays imposed by its own institutions. Bureaucracy can enable discovery through funding and infrastructure, but it can also smother momentum at the worst moments. And this episode has highlighted both sides of that truth. Whether 3 I/Atlas turns out to be a comet unlike any other, a rocky fragment from shattered world, a metallic relic sculpted by deep time, or something we have not yet imagined, it has already done something extraordinary in the present tense. It has made people look up together, united in wonder beneath the same sky, and reminded the world that the universe is still capable of surprising even the most advanced civilizations, leaving us to ask again, with fresh urgency, what else might be out there.